mechanical design of the CanSat is developed using Autodesk Fusion 360. We sketched a base PCB layer maintaining the diameter and thickness of actual PCBs. The electrical and hardware components were manually designed as well as imported from outside sources for convenience and accuracy. We designed the nuts and screws that add to the physical integrity of the model. The physical materials of the components were chosen according to real-life scenario. The weight of the entire payload and the container adds up to approximately 547 grams, which is viable as per the competition rulebook. The container is designed with a removable lid with a diameter of 123 mm and length of 226 mm that fits the entire payload of our CanSat. We went for a round-shaped PCB structure and cylindrical container so that we don't leave any scope of developing sharp edges. Right now on screen you can see our entire design unravel itself. The container that holds the model is made of a hollow plastic can with a lid attached to it with screws. The lid is removable for the ease of access to the power switch. The fourth layer is made of a double layer PCB that holds Neo 6M GPS module, the GPS antenna and MPXB7002 differential pressure sensor. The GPS module output gives the latitude, longitude and altitude of the drop point as well as the date and time of the drop. The GPS antenna is connected to the module using a copper wire. The differential pressure sensor MPXB7002 is connected to a pitot tube using two more connecting tubes at two ends. The tip of the tube is placed outside the container by drilling the container body. The differential pressure sensor output is used to calculate airspeed of the drop point. This layer houses the power switch which is connected to the power supply in the bottom layer. The third layer is equipped with sensors and an accelerometer. We used LM35DZ temperature sensor and MPX4115A pressure sensor and ADXL345 accelerometer. The JPT pinholes of the PCB connect all the electrical components to the Arduino. The second layer holds the microcontroller, radio communication module and camera module. Here we used Arduino Nano, APC220 radio module and ArduCam mini camera. APC220 provides us with wireless communication to our ground station. The antenna is screwed to the module. The camera that we used is a 2 megapixel sensor that captures picture during the drop. 3 LEDs are used in this layer that are visible from the outside and indicate operating conditions and battery performance of the CanSat. Then finally, the first layer holds a 9-volt alkaline battery connected to a single layer PCB via a battery cap. A voltage regulator IC7805 is used in this layer to get a constant 5-volt output voltage to the microcontroller. The battery is stored inside a box which is mounted to the base so that there is no chance of disconnection during or after the fall. A screw terminal has been used in this layer to route the power cables to the upper layers. Last but not the least, the hardware components include a set of plastic wires and wire covers and a couple of metal stands holding all the 4 layers. The wire covers protect the wire from any damage and also adds to the structural stability of the design. The stress-strain analysis of the model was done in the simulation environment of Fusion 360. The analysis was performed individually on 4 PCBs and on the bottom of the container. The applied loads are calculated from the mass of the components of a certain PCB. These loads are applied on the faces constraining the support stands and we got positive results. The designed model can safely withstand the applied load without any visible deformity. We performed several analyses on the bottom face of the container with arbitrary impact force magnitude and found out structural strength of our design.
As we have no real-time data to perform any GUI analysis, we went for an illustration-based design for our ground station. The ground station is expected to provide us with 2 types of views, one HUD view and one data view, which gives us a thorough representation of our sensor data. The ground station is equipped with a camera view that is expected to present pictures taken during the drop. The ground station will connect the GPS values from the module output to maps and is expected to present the location.
We used hex nuts and screws to mount the electrical components and modules for a rigid structure. The wires between the layer is expected to be soldered. Moreover, the wires are protected with plastic wire covers that minimizes the risk of wire damage and disconnection. The battery is kept inside a battery box to maintain its position during the fall.
The electrical schematic design was done using Autodesk Eagle software. The circuit components are circled around the microcontroller Arduino Nano. The electrical components were chosen based on their availability in local market, cost, and weight. We went for a PCB approach instead of direct connection to minimize the use of jumper wires. The PCBs are also designed using Eagle, and the components are placed on the PCBs in such a way that the load is balanced throughout the area. The layers are connected via 10 JPT pinholes in second, third, and fourth layer to connect all the sensors and modules to the microcontroller. The LEDs and camera lens is placed near the edge of the PCB to make them visible from the outside.